Hello students, this is the second video which we are doing. In the last video we had summarized the mathematical concepts we had learned so far in module 3. This is a short video so as to recap the physical concepts, the concepts of physics, how they were put into the language of mathematics. In this video we shall briefly review them. Let's start. So the fundamentals which you must know are electrostatics and magnetostatics and the other things. As the lecture progresses, we shall discover which are the laws and how they will be put into the mathematical form. We will start with the Coulombs law. What does the Coulombs law say? If you remember, Coulombs law says the force between two charges, it could be Q1, Q2. Okay, Q1, Q2. The force between any two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. This is what Coulombs law would say. Right? This is how Coulombs law is expressed. But for simplicity, if we assume that Q1 and Q2 both are equal, which is equal to Q, it will be F is proportional to Q square divided by R square. Okay, so since it is proportional, in order to convert a proportionality into an equality, we have to insert a constant. And what is that constant? In proper dimensions, it is called 1 by 4 pi epsilon naught. Okay, what is the value of 1 by 4 pi epsilon naught? 9 into 10 power 9 units. Okay, this is the Coulombs law. This is the content of the Coulombs law. This is what you already know from your pre-university classes. Now, moving further, see, this is Q square. I have assumed Q1 is equal to Q2. Okay, if I say that Q1 is not equal to Q2, what will be this law? It will be equal to F is equal to Q1 Q2 divided by 4 pi epsilon naught R square. Now let me cross multiply this Q2 here. This will be F divided by Q2 because F divided by Q2, and set that Q2 is equal to 1 coulomb unit of 1 coulomb. So what will happen? This is force per unit charge. This is Q2 I have set Q2 is equal to 1 coulomb. So this is force per unit charge, and this quantity is what is known as electric field intensity, or simply electric field. And what is it given by? Since I have cross multiplied one of the Q's, it is only 1 Q here divided by 4 pi epsilon naught R square, and this is what is known as electric field. And what is the message of this equation? The message of this equation is wherever there is a charge, it becomes the source of the electric field. Okay, this becomes the source of the electric field. But if you remember here, there is something called epsilon naught here. What is epsilon naught? Epsilon naught is absolute permittivity of free space. What is the absolute permittivity of free space? 8.854. Suppose that these two charges are not there in vacuum, some medium is in between these two. Now how will you write this? Instead of epsilon naught, you have to write what is known as epsilon, which is the most generalized form. And this epsilon is a product of epsilon naught and epsilon r. For vacuum, it simply reduces to epsilon naught. It is because the relative permittivity of free space or vacuum is equal to 1. So this will go off. That's why you can write epsilon naught r square. In general, this is 4 pi epsilon r square. Okay. So when you cross multiply this epsilon here, this will become E into epsilon. This is called electric flux density. And the definition of electric flux density is D is equal to epsilon into E, where epsilon is the permittivity of that particular medium, which is the product of absolute permittivity and the relative permittivity of that medium. Relative permittivity of vacuum is 1. For different media, this number will be different. Okay, so this is the content of the Coulombs law in brief. So what does it say? It says wherever there is charge, it produces electric field. That is the content. So if you come to the magnetic field now, there is a similar law, not exactly similar, but the main law which deals with that is, here we had electric field intensity. Here the analog of that is magnetic field intensity, or just the magnetic field. It is represented by the letter H. Okay, so Biot-Savart's law say this is something which you already know. So this one dH or dH, or suppose that this is the small elemental length and you want to find out what is the field here due to this elemental length. It is given by I dl sin theta divided by r square. And remember, what is this I? I is nothing but dq by dt. What does it mean? It means it is the rate of flow of electrons. So once again, in order to convert a proportionality into an equality, you must insert a constant. And what is that constant? That constant is mu naught divided by 4 pi. Here it was 1 by 4 pi epsilon naught. Here this mu naught is analogous to epsilon naught here. This is called permittivity. This is called permeability. How much magnetic field lines are permitted or permeable into that medium, that is what decides this one. So here it was epsilon is equal to epsilon naught into epsilon r. Here mu is equal to mu naught into mu r. Here epsilon naught was 8.854 into 10 power minus 12 units. Here it is 4 pi into 10 power minus 7 units. Here the equation was electric flux density is equal to permittivity into electric field intensity. Here B is equal to mu h. This is magnetic flux density. Mu is permeability and H is the magnetic field intensity. This is a clear correspondence between magnetic and electric fields. The takeaway from this equation is wherever there is charge, it will produce magnetic field. This is a stationary charge. This charge is not moving. Here I means rate of flow of charge. Remember, current is rate of flow of charge. Whenever a charge is moving, if it is not moving, I is 0. So this one is 0. If the charge is moving, that produces the magnetic field. That is the takeaway from the Biot-Savart's law. I hope this is clear to you. With this background, now I think we can go to the preliminary form of the Maxwell's equation, and this is what we had discussed in the class. Okay. So first one, how does the first law of Maxwell come? This is the first law. How does this come? Where does this come from? This comes from the content of the first this one plus the Gaussian surface. What is a Gaussian surface? Suppose you have a charge here. Okay. Now, according to whatever we have discussed, what is the charge supposed to be? This is the source of electric field. Okay. So this disseminates electric field in all the directions. But if this has a permeability E, you know the relation between D and E. This is how they are related. Okay. So now you can consider any imaginary surface around that. So consider a very small segment of that, very small segment of that. Let's call this as ds. This is the signed area ds. Okay. This has a magnitude which is equal to the area, and normal is the direction to it. This is vector or signed area, and I want to generalize how much lines of force, how much electric flux density is coming out of the entire surface. How do I do that? I know this much of electric flux density is coming out of that in a small area. How do I generalize? I can generalize it as d dot ds. This is the electric flux density in a small surface area ds. If I want to generalize it to the whole surface, I will take a surface integral. Since it's a closed surface, I will take a closed this one. So this imaginary surface of any shape and size is what is known as a Gaussian surface. Now, why are you getting electric field intensity in the first place? Due to the presence of a charge. So this equation tells if there is a charge, the surface integral of d dot ds along the whole surface is due to the presence of the charge. Okay, that is what this equation signifies. Right. Next, I want to generalize this further. If I don't have one charge, if I have a collection of the charges, whatever comes out of this surface is not due to one charge, is due to the collection of the charges, because each charge will have its own, each charge is also a source. So how do I do that? I have to put a summation. If I have n charges, let's say this is I is equal to 1 to n, it runs from I is equal to 1 to n, qi, it is the summation of all the charges is what is responsible for electric flux coming out of the entire surface. This is what. The further generalization would be, if I don't speak about the discrete charges, if I tell you that there is a charge density in the entire thing, in the entire surface, and what is charge density? Usually density is mass by volume. What is charge density? Charge divided by volume. If I consider a very small volume and that contains a very small charge, if you are given a density, how do you compute it? You just have to cross multiply this. So dq, small charge in any small elemental volume, is rho v into dv. But this charge density might be spread about in the whole volume. That's why I have to take a volume integral here. You know, yesterday we discussed about the Gauss divergence theorem, and what is the Gauss divergence theorem? It is the theorem which converts any surface integral into the volume integral. So how do I do that? I have surface integral on one side, I have volume integral on the other side. So I will take this surface integral and will convert it into a volume integral. This is what the Gauss divergence theorem says. So vector, any vector ds dot ds around the whole surface, if you take the surface integral, that will be equal to divergence of that vector in the volume. And if I just do this, this is dv. Okay, so this is d dot ds can be converted into this. You have to just replace a by d, you will get this and you will get this. Since there is a volume integral on either side, and since dv and dv are there, without the loss of generality, since it is true for any volume, this can be written as del dot d is equal to rho v. And this is the content of the first Maxwell's equation. And the physical import of this is electric flux density. Okay, this can also be written as, remember, d is, what is the relation between d and epsilon? This is d is equal to epsilon e. If I want to write it in terms of e, then this is del dot epsilon e. So epsilon I will multiply here. This is rho e divided by e. This is the alternate form of this. What does it say? It says wherever there is a collection of charges, that becomes the source of the electric field. That is the import of the first Maxwell's equation, and this is the first Maxwell's equation. So he took the Gauss's law for electrostatics and put that into the vector formalism, what we learned yesterday, and that is what gave you the first Maxwell's equation. Now let's move to the second. After electrostatics, we will move to the magnetostatics. What is the same thing if you apply for the magnetic field? And please remember, in the magnetic field, if you take a bar magnet, for example, I am just simplifying. What are the sources of magnetic field? It could be current, because as we saw in that Boyd-Savart's law, a current flowing, a charge in motion produces the magnetic field, and magnet is also produces magnetic field. In fact, magnet produces magnetic field there because there are atomic currents. That we will keep it aside. But if there are in the magnet, let's look at the magnet. It starts from it is assumed that it starts from this is like magnetic lines of force start from here and come back. So they form closed loops. Okay, now if you consider any surface, it may or may not contain the magnetic lines of forces. We always know that magnetic lines of force or magnetic fluxes form closed loops. So total outward flux which is emitted by this is equal to total inward flux which is received from this. So what is the total? Whatever is emitted by this will be absorbed by this. So that is true for any Gaussian surface. Around any Gaussian surface, even if there are sources, they form closed loops. So whenever there is no closed loop, it is going forever, right? So if there is a source, this becomes the source. Here the source and sink are fused. So whatever source emits, that will be taken back by the source. So in this scenario, for any Gaussian surface, whether it may or may not, since they are forming the closed loops, the divergence of B is equal to 0. What does it say? It says that here there can be isolated positive or negative charges. Here there cannot be isolated north pole and south pole. That is the physical content of this. The non-availability of magnetic monopoles is what is signified by the second equation. Okay, so this is Gauss's second equation. Del dot B, the divergence of B, means sources and sinks come together for the magnetic field, or there cannot be the isolated north pole or a monopole. There can be electric monopoles here, but there cannot be magnetic monopoles. This is what is the content of the second law is. Now the third and fourth law. Third law is a something which comes from the Faraday's electromagnetic induction. As you already know, what is the Faraday's law? Whenever the magnetic field is changing, the flux linked with the coil changes and an EMF is produced. So EMF is directly proportional to minus d phi by dt. Actually, this is called Faraday-Lenz law, right? So the Lenz gave this sign. So d phi by dt. What is this phi? This is the flux. Okay, this is the magnetic flux. Rate of change of magnetic flux is the EMF is produced directly proportional to minus d phi by dt, and this is the law which is under consideration now. Okay, so you know that I will not go into details as I have told this in the class. What is EMF? EMF is nothing but it is the work done on a non-conservative force. It is the work done on a, to bring a unit positive charge around that circuit. How can you write that? If the circuit has certain length L, it is the line integral of E dot dl. This is how the representation of EMF is. And what is d phi by dt? Why is there a rate of change of flux? It is because there is a time variation of magnetic field dot ds. Okay, so if you put this here, the left hand side and the right hand side. Left hand side is EMF is represented by this, and right hand side is represented by this. And when you put it here, this is how it looks like. Okay, E dot dl is equal to this. So on one side I have a line integral, on one side I have a surface integral. What should I do now? I will convert line integral into a surface integral. How do I do that? Using Stokes theorem. Remember, if there is a vector A dot dl line integral along a closed path, that is equal to curl of that particular vector along the surface. This is the relation. I have a line integral here. I will now convert this into the surface integral. Instead of A, you have to put E here. So del cross E dot ds, I have converted this into this, and right hand side is as it is, minus del B by del T into ds. Since there is surface integral on both sides, ds and the ds, without the loss of any generality, I can now say del cross E is equal to minus del B by del T. What does it say? It says the curl of electric field is equal to negative rate of change of magnetic flux density. This is the content of the, so this is the relation between electric and varying magnetic field and the electric field. The circulation of the electric field is equal to negative rate of change of magnetic flux density. This is the third one. And third equation of Maxwell. And the fourth equation of Maxwell, this is the last part which we have already discussed. I will be very brief. So it is partially from the Amperes law, and it is this law which he makes a correction to. That we shall deal in the next class. Okay. So, but what is the content of this Amperes law? How did he puts that into, how this form is achieved? It is by this. Amperes law states the circulation of the magnetic field strength or magnetic field intensity along a closed path is equal to the net current enclosed. Enclosed is, if this is the path, there could be many currents here. It is called I enclosed. For simplicity, I am just taking one wire which is conducting current. So it's put mathematically, circulation of magnetic field, if dl is the small element, if you take the line integral around this will be equal to I enclosed. Okay, but remember, we defined in class, there is something called current density. Okay, what is current density? Current per unit area. Area is a signed, this is a signed area, this is vector. So if you cross multiply, I can be expressed as J into dA. If I don't take A instead of this, I will take a small differential area. This is called ds. So when I cross multiply this, what will happen? I will be equal to j dot ds. This is just simple mathematics which I have done. Instead of I enclosed, what should I write? It is the surface integral of, because this is the small surface area, I have to generalize it to the whole surface area. This is the small area. So generalization of j dot ds to the whole this one. So this will be the equation. Line integral of h dot dl is equal to surface integral of j dot ds. Now once again use the old trick. There is line integral on one side, there is surface integral on the other. So you can convert this line integral to the surface integral using Stokes theorem. So line integral of a vector a dot dl line integral is equal to del cross a, curl of a along ds. So I will convert this into this. H becomes del cross h along ds and surface integral of j dot ds. So without the loss of generality, what I can write, since the integrals are same on both sides, del cross h is equal to j. This is the fourth equation, and this is what Maxwell finds to be something incomplete, and that is something which is the greatest achievement by Maxwell, and that is what we shall do in the next video. Thank you for watching.